Okay, well, I'll just go ahead and start the recording, and we can talk. No one else has joined in yet on Discord, so we can talk about the asynchronous stuff.
Yeah, I don't even know where I went wrong, because I know I asked you, like, right before the exam, and then it was also, I think, almost the same as, like, homework assignment.
Very similar, at least, yeah.
But for some reason, I understand we're at the latch level,
Yeah.
and then I set it up like this. I don't know why this isn't right, though. Because she said not asynchronous, but I thought I made it asynchronous by saying the reset would, like, putting this extra reset.
So where did you? I think what she wanted to see was like the actual internals of the latch and what you'd edit. Because here, well, so you were basically trying to say, okay, this is what I would do in a truth table, but you didn't draw the schematic. The schematic you drew was a synchronous resettable.
Oh no, did I mess this up?
Because over here, that's the register, and then you just have stuff going in. So it's got to be synchronous because you haven't actually dived in and changed the internals.
Oh, I thought I changed it by adding in the second reset.
Well, no, that is going to make it resettable.
Okay.
That's right. But the issue, which is what she said, is it's not asynchronous because you haven't shown what you've done to the internals of this flip flop.
I see. I think I see. Okay, so I need to actually. So this is okay. Do I need a clock 0? Because I was thinking, like, okay, clock 0, and then it doesn't matter any of this. And then we're gonna wait. Okay, when for latch, a D-latch, we don't have a clock. So, do we even have a clock? I think this is where I'm like, don't understand what's going on.
So there is a clock input for both of these.
And this is wrong, right? Because the latches, I thought, didn't have.
Yeah, I think typically you don't put
Can't
that.
do that, yeah.
It doesn't really matter. It's just a drawing. But typically, that corresponds to meaning it's edge triggered. But the device as a whole is edge triggered. Each individual component is not.
Okay.
Or positively edge triggered. So what you'd want to do is you'd want to open up this box here
Okay.
and say, what's the inside of that box?
And that was where I was like, okay, if there's no clock, we get Q previous, and then if there's a clock, Q gets D. I literally wrote all of these different types like 8 times to try to memorize them.
Yeah, I can go ahead and draw it up on the board, or draw up part of it on the board.
Ooh. I don't know why this is so difficult.
Okay.
Oh, it's a little.
There we go.
Oh, yeah. Yeah, because here was my D-latch, which is basically our built over the SR.
So this is the D-latch.
Yeah.
This whole thing is the D-latch, yeah?
Yes. Okay. And yeah, that's what I thought. I was modifying the D-latch by putting that extra reset and the enable in there.
Mm-hmm.
And then this was going to be like my S and my R and my Q. Apparently that's not right.
So I think, here's my guess. To me, like when I look at this, it's possible she thinks this is the register, literally this is just the entire register, rather than this is an SR latch, and this is the first SR latch. That's a possibility. So...
Because I thought by doing SN and RN, I was making it, and like being like, okay, I'm going to do latch. I'm going to see her tomorrow as
Okay.
well.
That's a good idea to ask her about it, but
Yeah.
let me go ahead and... Well, actually...
Yeah.
So you just came in on the Discord. Sorry, I didn't see that. No homework due tomorrow, but you guys are doing test corrections, right?
Yes.
Okay. Did you have any particular questions for me? Or are you just coming in because office hours?
Yeah, I'm just coming in for office hours.
Fair enough. Okay, so we'll go and talk about... We're talking about question 3 on the exam, which was the one with the asynchronously settable and resettable flip-flop. Is sign. So I'm going to go and start drawing some stuff on the board. Okay, so we have the asynchronously settable and resettable flip-flop. You break that into two pieces, which are the two D-latches, the two back-to-back D-latches. If I recall correctly, it goes backwards. Yes. Okay, so those are each of our D latches. So I'll call this D F or D flip flop. This is your D latch 1, D latch 2. And then whenever you're trying to edit the internals of these registers, typically you open up even the D latch and look at the SR latches inside of them. So I'll just open up this leftmost one. Okay, I'm going to go ahead and check to make sure this matches up with the one that you guys have in lecture, because there are different implementations of flip-flops, like you can make them differently. So I'm going to check to make sure this matches up with what you guys have, just to be consistent. On the top. I'll switch that around then. It doesn't matter too much in terms of the actual functionality, but just to be consistent. Let's see.
If you want to see.
Is that one? Yes. So there's a particular example though that she has, and I think it's drawn in differently for the when you separate the D latches.
Oh.
And in fact, I think it was actually that one. Sorry, this one. Yes, that's the one I was thinking about. So yeah, thank you. R is on the top. Q is on the bottom. That goes up here. This goes down there. And then you have. Okay, so I've gone ahead and drawn in our SR latch. Okay, cool. So we have two back-to-back SR latches where I've just opened this one up. And the inputs of this SR latch are D and the clock. As we can see from this diagram here where we have the D latch, we have D and clock as our inputs. And we basically just want to add a set and reset so we can edit these values, this R value and that S value there. So we're going to focus on each individual one, both ret and reset, kind of at the same not at the same time. We're going to focus on separately. You could do them at the same time, and you could do a truth table for it. That's perfectly fine. But just kind of like to build up to that, we'll do it just one. So I'll just focus on reset first to make sure that we have that down, and then I'll do it with both reset and set. Okay, so if we want to make this resettable, then what we need to do is we need to include just one resettable external signal that somehow feeds in and changes these wires R and S. And the general way we're going to do that is we're going to kind of come up with a truth table to figure out what circuitry we have to add in. So we're going to make a truth table for what this wire and this wire have to be, so R and S. Now, R and S have to depend on a few things, clock and D, as well as the external signal reset. So we could do our truth table like this, where we consider each of them separately, or we could just say, take a look and add in something here, which just depends on these two wires, instead of clock and D directly. So instead of editing everything that we have here, we can instead just say insert an extra gate or two. So I'm going to go with that second method, just to make this kind of as unmodified as possible. So I'm not changing everything around. So what I'm going to do here is I'm going to kind of open up my schematic a little bit more. And essentially all I'm going to be doing is taking my reset value and putting them into this black box. And what I want is for this to make it so that it's going to reset our SR latch over on the right hand side. So I have two inputs, the output of my D and clock signal being added together for each of these, and then my reset as well. So I'm going to be just using those, and I'll call this one maybe N1 and this one N2, and we'll focus on them separately. So I'll just focus on, say, the top black box. So, taking a look at that top black box, all I'm saying is that I have two inputs, N1 and reset, and then I have my output, which is called R. And so here's what I want to happen. I would like it for if the external reset is on, that I'm always going to have R go on, because that's going to reset my SR latch. And that is independent of N1, i.e. it doesn't depend on it, so it's a don't care. Recall that don't cares can also be written in a case-by-case basis. So what I have written up here is the same thing as these two lines down below. But just for conciseness, I'm going to write it just as the line up top. So no matter what this other guy says, no matter what N1 says, I'm going to reset it, if reset is on. Now if reset's off, then let's think about what's going to happen. If reset's off, then I'm going to take a look at N1, and that's just going to feed directly through to reset. If N1 says reset, we're going to reset it. But if N1 says not to reset it, and we're not doing an external reset, then we're not going to reset it. There is a slightly more concise way to write this truth table. And it would look a little bit like this. If reset is on, you reset. And if reset is off, then R is just going to follow whatever N1 tells it to do. So both of these truth tables mean the same thing. They do the same thing functionally, just different ways of writing it. And now the next step we're going to do, the next thing we're going to do is we're going to actually write out our equation for it so we can get our schematic. So I'll do it from this top one. So that first line says R is going to be equal to, well, it's true if reset is on. So say if reset is on, R is going to be on. Or, and the second line can occur if N1 is on and reset is off. Write that in 2. Okay. So I've written that equation, and there's one minor simplification I can do to it. What would that be?
Reset or N1.
Yeah, what theorem is that? Do you recall?
Simplification theorem?
Yeah.
you call it?
Yep. It doesn't really matter what they call it, but yeah, that's the simplification there. And so we have reset or awesome. Okay, so that means we can put that gate, exactly what I've written here, into this black box. And now that we've kind of gone through the logical process, let's see if this makes sense to us intuitively. So when do I want to reset? I want to reset if my external reset goes on or if my internal reset goes on. Otherwise, I'm not going to reset. Okay, so any questions about why this gate kind of makes sense for the reset signal? All right. So the next thing we're going to do is we're going to do the exact same process but for this guy. So essentially all we want to do is we want to make sure that because this is an SR latch, both of these don't go high. If they both go high, the output is undefined. That's what we found out when we first did SR latches. So we want to make sure that doesn't happen. And the way we're going to do that is we're going to basically prevent that case from ever happening using the fact that we know what this reset is going to be. Okay, so let's try it out. Something's going to go in here, and let's write up a truth table for it. Now, we're going to consider again, starting with the most basic case, if our external reset is on. If we're trying to reset the SR latch, what should the S be? So that we don't have any bad things happening. What do you think? I think that's pretty reasonable to say, yeah. If we had this be a 1, then we would get the case where R and S are both 1, and that's undefined. So instead we say, okay, if the external reset is on, S better be 0. Independent of what N2 says. Very similarly, we can talk about what happens if N2 is on versus if N2 is off, where reset is off. If N2 is on, that means we wanted to set it, and we're not doing an external reset, so we should set it. However, if they're both off, then we don't want to set it. So we say 0. And then we can go ahead and write the equation for this. So just looking at that first, or that second row here, we can say, okay, well, the wire S needs to be on if N2 is on and reset is off. And so that's the exact circuitry we're going to put in here. Okay, so you'll notice that I've drawn 2 reset signals. Those are the same thing. I've just kind of drawn them in separate spots just to make it easier to read the schematic. But those are the same reset signal. And here I've drawn in my gate that I got from my Boolean equation, which is N2 ANDed with the negation of reset, and that should be my set signal. Okay, so any questions about the process for how we make it asynchronously resettable? Because the next step is going to be very similar to this, just with a few extra steps to make it also settably, asynchronously settable. All right, so let's do it. I'm going to, again, erase these, do black boxes, and each of these black boxes is going to have set and external reset as possible inputs that affect things. So again, all I'm going to do is I'm going to ask myself, what do I need in this black box in order to accomplish my goal? So looking back at the prompt, essentially what it's asking for is for you to make it asynchronously settable and resettable, so you can do either. And the reset here is going to take precedence, which is to say if reset is on, we just don't care about what S is. So we're going to have to include that in our truth table derivation. And so I can go ahead and start writing that. And I'll start it with this top one up here. So again, just like I did before, I'm going to start with the box for R, and we'll do the box for S second.
And the set is the enable part? Is that what you were saying?
Oh, it's not settable and oh, never mind. It's not settable and it's enableable.
I mean, this is really helpful also.
I see. Okay, I misinterpreted this. I heard another student explain this one to me because I hadn't seen the actual problem yet. You guys hadn't gotten your midterm. And they said it was settable and resettable, but that's not what it is. It is asynchronously resettable, and it also has an enable input. So the fun thing about this is the enable input's synchronous, no matter what. And it's a little weird to think about why, but the reason why is because what is the purpose of enable?
So, this is just, I feel like it's to make it a routine.
So if enable's on, it behaves regularly. If enable's off, all that means is you're not allowing the register to read in on the positive edge of a clock. Because in any register, it only reads in on the positive edge of a clock. And so all enable is going to do is if it's off during a positive edge of the clock, you don't read anything in. So it has to be synchronous by definition because it only affects stuff on positive edges of the clock. So the nice thing about what we just did is we just made a synchronously resettable, or an asynchronously resettable SR latch, and therefore an asynchronously resettable D flip-flop. So I'm going to just redraw that circuit in one more time. And the reason why I'm drawing that circuit in one more time is because we can kind of modularize our design, think about them separately. So what we can do is we can say, okay, we've just made a resettable flip-flop. So I'm going to draw that off to the side. Right here, this is my resettable flip-flop, asynchronously resettable. Now I take this. I already have this. It's already done. I've already designed it from down here. Now I need to make this enableable. And because it's synchronous, I don't have to go into the internals. I can do this as external external circuitry, just as if I was making a synchronous reset or a synchronous set.
So sorry, our first step is this one. And then after
Now we add in the enable.
edge, now we just look at the enable.
Yes, because again, the enable only works synchronously because by definition, the register only reads in values synchronously. So here's what I'm going to do. I'm going to say, okay. I need to put a block of logic here that essentially makes it so that when enable's on, DIN gets fed through. So it behaves normally. But if enable's off, then I keep whatever was in the register. I don't change it. Okay, so let's think about how to do this. And in fact, I've actually drawn the way I've drawn this implies that there's only two inputs. There's actually going to be three. We'll get to why there's going to be three in just a minute. But I won't draw it in to see if you guys can figure out what that third one is while I'm talking.
Wait, sorry, is all of our SR latch is in now that right-hand side?
Yep. So this
Okay.
is all inside that.
Yep.
So there's two copies of this, and each of
This is
those
inside
are
that.
both inside.
Okay.
Yep.
Sounds good.
All right. So I'm going to go ahead and start writing up my truth table for this. And I'm going to make my truth table exactly as I've indicated verbally. So, DN, enable, Okay, so let's think about what we want to do if enable is on. What should the output be?
Output should be DN.
Yeah. So let's just write this kind of like I did for the other ones in a shortened truth table. If enable's on, D gets DN. Now what if enable's off? What am I supposed to do? Or what do I want to happen? What do you think, Good Noodle? What should I write over here if enable's off?
We want whatever Q was.
Exactly, whatever the previous value of the register was, which is to say, as I mentioned earlier, we have another input, Q. So I'll write it as Q previous, but it's just that wire there. And in fact, actually, I'll just write Q. So here's what I'll do now. I need to now write the equation for D. So I'm going to say, okay, well, D is on if, so in the first row it's on if DN is on and enable is on. So that's that first row. And then the second row says I'm on otherwise if Q is true and enable is off. And so now I can write out the equation for this, and now I can write out the schematic for this, which would look something like the following. And indeed, I'm going to need some more room. So I'm going to have two AND gates connected via an OR gate. And that's going to feed directly into my register, where this is D. So my first AND gate is going to be DN ANDed with enable. And my second AND gate is going to be Q ANDed with the negation of enable. And that's my finished circuit. So again, we made it asynchronously resettable by opening up that flip-flop into two D latches, opening up the first, well, it's both, you're going to replace this in both, opening up one of those D latches, changing that internal circuitry by adding these two gates, zoom back out and we say, okay, we have a resettable flip-flop, asynchronously resettable. Boom, we put that down on our board and we say, okay, now I want to make it enableable, which is by definition synchronous, so we don't have to mess with the internals. And we say, okay, how do we do that? Make a truth table, derive our equation, we put down our logic. So now let's go through a few examples and see how it works. If enable is on, remember we wanted this to behave just like a normal D flip-flop. So what that means is that the input of this AND gate is going to be what? Well, if enable is on, then the input of the AND gate would be off. So no matter what Q is, this is going to output 0. So when enable is on, when it's equal to 1, this is going to be 0. And so this OR gate is just purely dependent on what the output of this AND gate is. If this is off, then it's going to be off. And if this is on, then it's going to be on. And let's just take a look here. If enable's on, this AND gate says, okay, well, this input is 1. So whatever this input is, that's going to be my output. If this is 0, that's going to be 0. If that's 1, that's going to be 1. So DN gets fed through here, and DN gets fed through here. So if enable's on, D gets DN. And we can do a very similar exercise for if enable's off. If enable's off, again we say, okay, this is 0, that's 1. So this AND gate is going to output whatever Q is. Now here, if enable's off, this AND gate has a 0 at one of the inputs, so it's going to output a 0. And because we have 0 or something, the output is going to be that something. So if enable's off, D gets Q, or Q previous value of our register. So we've just assigned an asynchronously resettable and enableable flip-flop. And that's, I think, everything she wanted.
She said it wasn't asynchronous because I put it in with the reset, which would have made it.
Yeah, I think it's because you put both of them together.
Both at the same
And so, yeah.
I don't think I would have known that the enable was
Synchronous.
separate.
Yeah.
Synchronous. I thought everything was asynchronous, so I think that was my problem with that question. Now I know.
Now you know.
Good.
And now you know what an enableable register is.
Yeah, this was great. Thank you for explaining this.
Okay. Any questions about this process from anyone? Okay. So I'll go ahead and erase the stuff on the board. If there are any other questions, because I know the homework hasn't been posted yet, so if either of you have any questions about just exam stuff, that's fine too. We can go over other material as well, or maybe something you covered in class, if you guys have covered something in class new that hasn't been on the midterm yet, anything like that. So if you have any questions, let me know.
Yeah, I have a quick question.
Yep.
So now, what we will be going over now, it would be like the ALUs and like types of parts of like the CPU, right?
Shoot, honestly, I don't remember. I think so. You're going to go into that. But if I recall correctly, the next thing you'll be doing is actually assembly stuff. If I'm correct, you're going to go over all of that stuff eventually. You'll go over adders and carry look-ahead adders and ripple carry adders. You're going to go over assembly. I doubt you're going to go into like data path stuff. That's more 300, which is processor architecture. So you might cover that a little bit at the end of class if you guys have time. But that's a 300 topic rather than a 200 topic. What else? Yeah, I think it's mostly just RISC-V assembly that you guys are going to be going over. I can't remember what else is at the end. But that's like the next big thing you're going to be doing, assembly stuff.
Okay, thank you.
Yep. Okay. I guess while we're waiting, I can explain another kind of thing you can do to a register. So we've gone over settable registers, resettable registers, which kind of do opposite things. We've gone over just now enableable registers, and now I'm going to talk a little bit about toggleable registers. So the way a toggleable register behaves is if it's off, behaves normally, nothing changes. But if the toggle bit is on, then you're going to take whatever's in the register and toggle it. So if it was a 0, it's now going to become a 1, and if it was a 1, it's now going to become a 0. So the general implementation is actually very similar to the way we implemented enable. Almost identical, because we still have the same process of it behaves the same if it's off. And if it's on, it's going to depend on what my previous value was. The only difference is at the end there, I had a Q output and go directly into an AND gate. To toggle it, I have to just negate that. So actually toggleable and enableable use almost the exact same circuitry. You just invert the output Q before feeding it back into that logic. So let's see. We went over resettable, settable, enableable, toggleable. Those are the majority of the ones that, like the kind of things you can do with registers. You can toggle them, enable them, reset, set them. I'm trying to think if there are any other common operations, but for the most part, that's it. That should be it. And typically, if you see a register or a flip-flop that is toggleable, it would be called like a T flip-flop, something like that.
So toggle is synchronous.
Correct. Just like enable. Yeah. Okay, any other questions for me?
Yeah, I was taking a look at the syllabus, and it says that we create multipliers. Are we like using like Boost algorithm for that, or is there a different type of algorithm?
To make a multiplier?
Yes.
Well, it says multipliers. I think you're not going to actually be multiplying numbers. Well, you're definitely going to be able to make adders. I don't recall if you guys actually make multipliers. That might be referring to a slightly different thing. You're not actually multiplying two numbers. It has to do with taking a clock signal and deriving another clock signal from it. So if you have an input clock that's 50 megahertz, there's a standard way to bring it down to 25 megahertz, or to bring it down to, say, 12.5 megahertz. That's called a clock divider. You can also make clock multipliers, which will allow you to make not just like divisions by 2, by 4, by 8, but any value in between. And in general, that circuit looks something like this. So this is the clock that you're dividing. And essentially what we do normally is we have basically an adder. This is what this circuit is, denoted by the plus sign there. So this circuit adds two numbers. It adds this input plus that input, and then outputs on that wire. And basically what this is doing is every clock edge, we're adding on 1 to the register and feeding that in. So if the register started with the value of 0 in it, at the next clock edge it's going to be 1, and then 2, and then 3, and then 4 every single clock edge. And so what you can do is you can take this multi-bit signal and pick off some of the wires, and each wire is going to have a different rate of change. So say this clock went at this speed. We know that at every rising edge of the clock, the register gets updated with a new value. So the bottommost bit is always going to be going 0, 1, 0, 1, 0, 1, because we keep adding 1 every time. And every second one we add, there's a carryover to the next column, which is why it's switching 0, 1, 0, 1, 0, 1. Just like if you were counting in binary, when you go like this, 1, you'll notice that least significant bit is switching every single time. Whereas this second least significant bit is switching every 2, this one's switching every 4, etc. And so if we were to just consider this bit here and see its rate of change, what we would see is the following. If it starts at 0, on the rising edge of the clock it switches, and then on the next rising edge of the clock it switches back, and so on. If I told you the period of this was, if I told you the period of this was 10 nanoseconds, could you tell me what the period of that second clock is? Yeah, what would it be? 20, yeah. So we've just doubled our clock period, or halved our frequency. And so for this one, our frequency would be 100 megahertz. For this one, our frequency would be 50 megahertz. If you were to, instead of looking at the least significant bit, look at the second most least significant bit, you would see a similar pattern, except it would change every 2. So it would be, again, double this frequency, double this period, or half this frequency. So it'd be a 40 nanosecond period and a 25 megahertz frequency. And that pattern continues as you get more and more bits. So you can basically generate as small of a clock period as you want. And that's the point of this. Is called a clock divider. You're dividing it by 2, 4, 8, 16, etc.
Is the CPU 300?
No, it's 200.
Oh gosh. I was like looking through, I couldn't find the dividers or anything.
You should be able to. I'm pretty sure you guys are going to be going through it. At least I did when I did 200, so I imagine you will be. Oh, and then the reason why I brought this up is because this number here is actually called the multiplier. Because what happens is if you change the number you're adding here, it affects how often we switch. Because instead of counting by ones, 0, 1, 2, 3, you're not counting by ones anymore. You're counting by twos or by threes or by fours, and so that increases the clock speed. It's going faster now. Okay. And I believe that's what's meant by multipliers. That's referring to that number there. And so you'll be going over clock dividers as well. You might actually be going over the multiplier circuit. I don't know. I don't think I went over it when I was in 200, but it's very possible you will. I think it's in the book as well. Okay, any questions for me? You guys probably won't go over this for a little while.
If you were to have a problem that would like say like what's the rate of change, we would probably just want to take a look at the least significant bit first and then go up from there, right? Because
Yeah,
I mean, it
there's
stays
a
the
formula
same.
for this. I just haven't written it because I'd rather show you how to get, like, how to understand the circuit rather than just say, here's the formula, plug in the numbers. But you can directly use the formula, and it's going to look something like the following. So the new frequency is just going to be the original clock frequency divided by 2 to the n, where n is basically the bit you're checking. So if you're checking the bottommost bit, that would be bit 1. You would divide it in half, and so on. And I think actually, if you want to call this bit 0, call this bit 1, call this bit 2, you would say 2 to the n plus 1. I think just to keep it standard where you have that bit is 0, that bit is 1, that bit is 2. So that would be the general formula to find what your new frequency would be depending on which bit you select. And just like I mentioned before, every consecutive step you just divide by an extra 2, which is why I have 2 to some exponent here. So it's just whatever your original frequency is divided by 2 to the power of whichever bit you're on here. So again, if you're on bit 0, that'd be 2 to the 1. So frequency divided by 2, which is exactly what we saw before, because this was bit 0. For bit 1, it'd be 2 to the 1 plus 1, 2 to the 2, or divided by 4, which again is what we mentioned when we said, okay, if you look at this bit, it changes that. It has half the frequency of the one that came before it. So yeah, there is a general formula for it, and you would use that if you were asked to find any bit rather than just say, okay, divide by 2, again, 70 times. You would actually just plug it in.
Okay, thank you.
Yeah. And this value here actually does go in the equation. I have written it here implicitly, like this, assuming that we are adding 1 every time. But in general, the multiplier goes here. So whatever that multiplier is, it's going to go in there, and that'll give you your frequency. And the explanation for this is basically just, if you're adding 2 every time, you're changing at twice the rate. So whatever your frequency was without that, now you've doubled it, or you've tripled it, or you've quadrupled it by adding 3s every time, or 4s every time. But again, you'll go over this later on in the semester. You will go over how to make these adder circuits, how to do a full adder, and then to make multi-bit adders, which is what this is an n-bit adder. You'll learn how to make multi-bit adders using chained full adders, which is called a ripple carry adder, and you'll learn how to do it with propagate and generate signals, which are called carry look-ahead adders, as well as delays through them and stuff, and why you would want to make a carry look-ahead adder instead of a ripple carry adder, what the benefits are. You'll go over timing delays and things like that as well.
Should be next.
That's the next thing?
Well, it looks like adders, ripple carry subtractors
Yep.
was on the docket for week 4, but I think it obviously got pushed out.
Yeah. And then after that is the assembly stuff?
Yeah. and then
Comparators, yeah.
Week 6 after the midterm, C programming, counters, and then risk 5.
Yep.
Yeah, but I don't think subtractors and adders. I mean, we did it in the lab. We did an adder, and we've gone through we've gotten to that part in the book. So I think that's like chapters 5,
Mm-hmm.
maybe.
That sounds about right, because chapter 4 is
The Verilog.
Verilog stuff.
Yeah, and 3 is the sequential.
Yeah. Okay. Any other questions for me? Are you guys both taking lab?
Yes.
Have you thought about what you're going to do for your final projects? Because you get about 2 weeks from them. So if you start thinking early, you'll get a head start and you'll be able to do it faster.
I think my lab partner has an idea, like that he really wants to do, so I'm fine with that. Because he took it 2 semesters ago. but
Is his
never
name
dropped it.
Mason?
No, Jonathan.
Jonathan. What's the last name? Baker?
Yeah. Isn't that like, I know, it's like.
Well, that's one of the professors, yeah.
Yeah,
I
and
don't-
that's why when I first emailed him, I was like, are you sure this? I'm joking.
No, I believe you. I believe you. Well, anyways, it'd be a good idea to think about what projects you want to do, and maybe even start on them if you have time.
Yeah.
Um,
Because we'll have to write our own test bench for that, right?
yeah.
Yeah, that's kind of why I was asking, I think, yesterday. Like, I'm a little nervous about that part. Because before you went through it, I didn't really know what was, how it was made or anything.
Yes. You'll go over test benches in class too, so it's fine if you don't understand them fully. If you even got 20% of the stuff that I went over, that's perfectly fine. Because you'll go over them again in class, and you'll be going over them a bunch of times in lab too. You'll have to do them for your final project, so you'll get plenty of practice with them.
Does CPE 200 get to work with like creating graphics onto a monitor, or is that CPE 300?
Yeah, you can definitely do stuff with the VGA. Yeah, you're gonna have a lab
Okay.
doing stuff with the VGA as your last lab.
I see.
It's very like basic. It's not. It's just like when you do the lab, it's just putting blocks of color and like letters on the screen, and there's intricacy into how you can actually make graphics, very rudimentary ones, and how you can make a module that controls them. But that's something that is best left to be experimented with, rather than me to explain how they're done immediately. But yeah, you'll go over those as your last lab. And not everyone does VGA stuff, but most people in 200 Lab do something on the VGA just because it's cool. People like to do it. Doesn't mean you have to, though.
We've done, I think, 4 labs. There aren't many, though, this semester. I think there were only like 8 or something.
Yeah, that sounds about right.
Yeah, I think we're like a good chunk of the way through, which is crazy. Time flies.
Yeah, it does.
Oh, we've done 3. No, 4. Nine labs. We only have 5 labs left. And our next lab is ALUs and test benches.
Okay. Since we have 10 minutes left, I guess, if you have questions, please interrupt me, like if you have ones you want to talk about in class. I said that if it was desired, I could talk a little bit about I don't have the time to go through the whole problem, but I could talk a little bit about the interview question I was asked, which was an FSM question. That was a little bit intricate, and also we had to code some stuff up for them. We had to make a clock generator, we had to make the actual FSM, and then show that it worked using a test bench they had for us with some given inputs and things like that. So I just want to...
For the TA position?
No, for...
Or your internship?
Yeah, for an internship at a place called Aldeck in town.
Yeah.
There was no interview for the TA position.
Oh,
Dr.
really?
Harris just asked me if I wanted to be the TA.
You've proven yourself already.
Yeah.
Sure.
So, I'll go ahead and briefly talk about like the prompt. I didn't bring the actual paper because I left it at the place, but I have kind of like a rundown of generally what they wanted. So,
Wait, and I'm sorry, when did you do this? Were you past CPE 200?
oh, this was like 2 weeks ago.
Oh, okay. Okay, so you're already like very knowledgeable. I feel like, oh my gosh, if somebody has knowledge or if someone interview right now,
I mean, the whole point is
freeze up.
they wanted to know like the general process for doing it, rather than like getting an actual like finished thing. Because we only had so much time. We had already been there. I think the interview was about 4 hours, so we had already been there for like 3 hours, and we had about an hour for the last thing. So they were fine if we kind of just explained to them our process. I went through the whole thing and like simulated it, and it worked. So I was happy with that. But again,
Had, like Quartus in front of you.
it was
and
Model
Sim,
Sim, yeah.
and-
Or it wasn't Model Sim, it was... so Model Sim you guys use, but there's another software called ActiveHDL, which is that company, Aldex. It's their software, just like Model Sim. They do a lot of stuff in VHDL, another language, kind of like System Verilog. They're both hardware description languages, but just syntax stuff is different. But for the interview, they let me write in System Verilog, so it doesn't matter. Anyways, off topic. So the actual FSM question kind of went like this. And you weren't told it was an FSM, but you can kind of reason it out based off of the way that this is worded. Because it's supposed to be a control system. It's supposed to control a door. And in order to control things, typically you need an FSM. So the prompt was basically like this. You have a door that you want to be able to unlock with a key card. And a key card is represented by a 4-bit parallel input, which basically encodes what that person's key card is. And if it matches the correct number, which is, in this case, I think it was 6, it'll open the door. And then if you scan it and it's the wrong key card, then that means that you don't open the door. And if there are 3 incorrect scans back to back, then you're going to sound an alarm. And the alarm is going to keep going until you have the correct key card. Scan it again. And then it'll enter the locked state. It won't unlock at that state, it'll lock. It'll still be locked, but the alarm will come off. So that was like the basic gist. And then there was an additional component where you could have the alarm on for exactly 60 seconds and then shut off without having the key card. So that was like the overall design problem. That's basically the prompt. And then it's now your job, given that prompt, to say, okay, that's a lot of stuff. What are the things that I need to break this down into? What are my steps that I need to take? So, and one other thing. So I mentioned the alarm. If you open the door, instead of the alarm going off, you're going to have a light turn on, basically signifying the door is open. So that was the other thing. So, with that in mind, what's the first thing you do with FSM design? What's the very first thing? Black box, yeah. What are my inputs? What are my outputs? Okay, let's see.
This is fun. I love working through like a real problem because it's similar to that garage door opener example we have.
Yeah,
but,
it
like,
is.
with a lot more stuff
Yep.
involved. I'm very interested to see how this plays out.
So it's an FSM. We're going to need a clock. That's kind of just ingrained in any FSM, so I'm just going to leave that up there. Okay, what are my inputs? What are my outputs? According to my description.
So you said it was like a 4-bit, just 4-bit input on a key card.
Yep. Okay. And then what are my outputs, or what is my output? Yeah, the alarm. Yep. We'll worry about the 60-second thing later. Yeah, that was like a bonus part of it. So don't worry about it right now. And, even then, and the way they described it to us, they specifically mentioned, and this is a good thing for any design, start simple. Don't try and implement everything at once. You can do it, but when you have a very complicated system, it's often easier to think about modules and little pieces coming together to build one cohesive unit, as opposed to trying to get everything done at once. Here, you can definitely do it. Try and get everything done at once. It's just a little harder than thinking about individual steps. So that's our inputs and our outputs. And one small thing is you might mention, well, you don't have an output for the door to control the door. And while it's true, you could totally have an extra output for that. The fun part is, actually the signal to open and close the door is the same as the light signal, because the light's on when the door is open and the light's off when the door is closed. So actually these are the same, which is why in my design and in this one, I'm not going to have a door open signal. It's just the light signal, because they are one and the same. If I really needed two separate wires to carry that information, I would do this. I would literally run one wire to the light and one wire to the door control thing that opens the door and closes the door. A few other details. When the key card is 0000, that isn't actually a key card entry. That means that there's nothing being swiped right now. So 000 corresponds to no key card.
Wait, I'm sorry. So when you say key card, is it like an encoded key card, or are we pressing a button and then swiping something?
Like an encoded one, where you just wave it in front and it opens, kind of like the doors here.
So our default is like 000.
Yeah, that means there's nothing present on the scanner itself right now. And if it's any other value, then that means that there has been a key card that's been swiped. Or scanned, pardon. Okay. So, what would be the next step? We've just drawn our black box. What do we do next?
Well, I'm just curious, and I think this is like my main question for everything is like, how do you decide between whether you want a Moore or a Mealy FSM?
That's the designer's choice.
Yeah, I know like obviously Mealy you have one less state, but like how does that translate to like fastness or like efficiency or like?
Well, in terms of efficiency, you would be considering like how many gates you're. So, if you have one less register, is that better than having the additional output logic gates that you need to have? So, is it more costly to have a register versus those output logics? And the same thing for your encoding. How are you going to choose your state encoding? Are you going to do binary or are you going to do one hot? Binary means you have less registers, but one hot means your output logic is reduced. So it's a very similar concept. And it just really depends on the problem and what your constraints are. If, I don't know, you needed more, if you have a very small chip that you're designing this on and like area is a constraint, you'd want to go for whatever thing has the least amount of physical area for all your things, and that would play into considerations. There's many different things. For this though, and just like for a general problem like this, if you're not like in a job trying to design the PCB that has this circuitry on it, just decide. It doesn't really matter too much. For mine, I believe I did one hot encoding and as a Moore FSM, just because Moore FSMs are typically what's used. Just in general, like 95% of FSMs are Moore. So here's what I'll do. Next time, if we want, I can go over kind of the design I went through this. I wanted to propose this problem so that you guys had a chance to, if you wanted to, do some of it or think about it by yourself. And so you can think about what your answer would look like. And all that I would really want is like a diagram. You don't have to go into the schematic process, just the diagram. Because, yeah, just the state transition diagram. Because after that, it's kind of rote. You just follow the pattern and you transform that into tables, and then transform the tables into equations, and then the equations into a schematic. And there's no real creativity in that last step. The real creativity comes in making the diagram. And we could also go over, after the diagram, how to write it up in System Verilog. We can talk about that too. Just how to do FSMs in general, because I know you guys have gone over that in class, but it's always nice to just do more examples. Okay. Any other questions for me about constraints about this problem before you think about it? 'Cause I think that was everything that you need to know. Let me check.
What was the correct input for the key card?
Oh, 6. Thank you. Yes, it was 6. But you can actually choose any, or if you want to make your design more complicated, maybe do multiple. Maybe 6 and 10 are supposed to work. But yeah, for our problem, it was 6.
6 and 10, you probably want the factor.
Yeah, you might want to do a factored. It's possible. I think, though, actually, it'd be better if you didn't, because of, well, you'll see. I think it would be easier if you didn't do factored.
I'm confused where the whole. Okay, so you said the outputs. If it opens, there's a light. If not,
If it's
there's an
closed.
alarm.
So,
Well, if you do it 3 times, there's an alarm.
yeah.
3 incorrect times, you output an alarm.
And the alarm keeps going until you get a correct keycard swipe. And if you get incorrect keycard swipe during that time, it's not going to do anything. It's going to keep alarming. Let me think. Oh, there was actually one other thing I didn't mention. So I mentioned that if you swipe it and it's locked, it's going to unlock with the correct keycard. But if it's currently open and you swipe it again, it's going to lock with the correct keycard. If you swipe it with the incorrect keycard while it's open, it's not going to do anything. It's going to remain open.
Okay, if open, incorrect, locked.
So basically, if you swipe it, it's going to toggle the state of the door, if it's easier to think that way.
Wait, if open and incorrect, it locks. Wait,
If it's open,
alarms.
if it's open and you misswipe it,
Yeah.
nothing happens unless you do 3 in a row, in which case, again, it's going to lock and then the alarm.
Okay. There's so much output. there.
Yes, there is.
Do we still draw it in the little circle?
Yes,
I guess.
yes, you do. Okay, so I presented this problem to you. Again, you don't have to actually run through the diagram if you don't want to. Just thinking about it is perfectly fine. We can talk about this more during the next office hours if we have time. I'd be more than happy to talk about it. But I believe that's all the notes I had written. If there are any other things you guys want me to clear up tomorrow,
Yeah, I
Or
like
another
this.
time.
I like these real world problems and I think it's great.
yeah, no, it is
I feel
nice.
like we're all gonna have something like this eventually, so it's good to get early exposure to it.
Yeah, exactly.
So.
All right.
Yeah, there's a career for next week.
Yep, yes, there is.
So. I don't even know what it is. I'm guessing that's Can I go home and think about it?
Yes. Yeah, it was something. It was a long interview, I'll tell you what.
So the first portion was like
So the first hour and a half, so it was a group interview, which is like there were 4 of us being interviewed at the same time.
all from UNLV.
Yeah, they
that's cool.
only hire interns from UNLV.
Oh, very cool. Is
And
this from Handshake?
no, actually they get recommendations from professors. That's where they get their interviewees from.
Yeah, that is.
What else was I going to say? Yeah, so the first hour and a half was basically just talking about our resumes. So they'd go around the table, ask us questions about our resume, stuff like that. And the next hour and a half was like a written exam they had. So it was 24 questions. The first 12 were like general STEM knowledge, math, physics stuff. And the last 12 were very specific to things you'd be learning in CPE. So visual object design stuff. Also a little bit of EE stuff like what is a transistor, how, and then they had a specific implementation question, I think for an FSM, but you just draw the diagram. I can't remember what it was, but very specific stuff that you would kind of be doing in class. And then after that, so that was 3 hours of that whole process, and then after that, they gave us the FSM prompt that they had us code up on their laptops and show that they ran. So that was the last thing that we did.
can I ask you? I know we're
No, that's fine.
hours, but there is. I've asked somebody else. So my cousin took like an engineering exam. Is it the FE?
Shoot, I know what you're talking about. To like get licensed as an engineer. Yeah.
Or PE.
Yeah, I think that's for mechanical or civil or something.
Yeah, see, he's chemical. This is at a different school, and so
Yep.
then I was like, should we all be taking it?
I think that's dependent on which type of engineering. I don't know what the license is called for computer or electrical. I'd have to check.
So none of the jobs you've been looking at like require any sort of licensing.
No. At least not in this field. Again, in maybe civil or electric or mechanical or something, possibly.
Okay. This is very helpful. I'll probably be picking it up because like
Yeah, that's
I'm
fine.
always looking ahead to like what I need to know. Start learning it now and studying.
Sounds good.
Alright, well thank you so much.
You're very welcome.
I don't I probably won't be on campus tomorrow, but I'll log in from home.
Sounds good. All right, you have a good one, and see you, good noodle. You have a good one too.
So, yeah, sorry. Just a really quick question about the FSM that you talked about.
Yep.
Since it's the inputs are parallel, wouldn't the light just be on if they swipe a correct key card? The alarm would be the one that we need to worry about, like the states they're in, right?
Not quite, because remember I said that if the door's open and you swipe, it'll close.
Oh, okay.
So the input doesn't directly correspond to the light being on or off.
Mhm.
It depends on
Okay,
what the
thank you.
current state is. So if the light's on and you get a correct swipe, it'll turn off.
Okay. All right. Thank you.
You're very welcome. You have a good rest of your night.
You as well. Thank you.
Okay, start